Hello, my name is Peter Sperfeld from the PTB in Germany.
And my name is Ralf Zuber from the company Gigahertz-Optik, also located in Germany.
And together we give you a short presentation on the characterization, calibration and use of spectroradiometers.
And in our talk we will cover different aspects. For instance, we will start with the definitions, coming then to different types of instruments for spectral measurements. We will talk about general requirements, the characterization of the most important instrument properties, and finally we will talk about the calibration procedure and some applications before we sum up everything. The aim of the spectroradiometric measurement is the determination of the spectral concentration. So this term spectral concentration isn't very well known, but this is more or less a description for instance, the relative spectral distribution, or the spectral radiant flux, which is given by watts per nanometer, or the spectral irradiance, which is given by watts per meter squared and nanometer, or spectral radiance, or spectral radiant intensity. In order to perform a spectral measurement, you need a spectrometer, so a device which is able to record a spectral distribution of optical radiation. A spectroradiometer, on the other hand, is an instrument for measuring radiometric quantities in a certain wavelength resolution over a given spectral region. So, in other words, a spectroradiometer is an absolute radiometric calibrated spectrometer. Very important are also the input optics, which are a part of your spectroradiometer system. So, for instance, if you would like to measure the total spectral radiant flux, you will need an integrating sphere as input optics. Here you can see the detailed description of this spectroradiometric measurement. Coming back to the input optics, we need to note that we have to design or select the input optics for the quantity to be measured. So thinking about spectral irradiance, which is given by watts per meter squared nanometer, we need input optics which allow us this measurement. In terms of geometry, we will end up then with some transmittive surface diffusers or transmittive bulky volume scattering diffusers or integrating spheres. So these designs are needed for the input optics in order to measure spectral irradiance. We can do the same for spectral radiance, and here we will end up with some imaging optics. So these two slides showed you that the input optics are very important for the measurement or for the quantity to be measured. Spectral measurements are of key importance also in the field of photobiological systems. For instance, to determine the blue light hazard by a weighting function. The same can be done for the erythemal hazard. Another application are photometer-based or radiometer-based measurements where a spectral mismatch correction factor is applied. So for calculating these factors, you need some spectral measurements. So we can sum up that spectral measurements are of key importance and also in the field of photobiological systems. On this slide, we show you some different spectral weighting functions. In yellow, you can see the erythemal function, which is defined from 200 to 400 nanometers. Interesting here is the high dynamic range when you look at the logarithmic Y scale. In black, you can see the thermal retinal damage, in blue the bilirubin function, and in red the blue light hazard function. So there are different weighting functions which can be applied to your spectral measurements. On this slide, we would like to show you the different instrument components of a spectroradiometer, beginning with the input optics as already described before. The next component is the fiber connector, which is actually optional. So there are devices where you need an optical fiber connector in order to connect the input optics to your dispersive elements or your spectrometer unit. On some devices, the input optics are directly connected to the dispersive element. Both have their disadvantages and advantages. Next is the detector, which could be a CCD or CMOS array. And finally, we have the software. Important here is that the software is part of your measurement system. So if you have a software update, you have to check that your software delivers the same results again. Coming to the typical types of spectrometer designs. On the left, you can see a scanning spectrometer in a tutorrial design. Number 1 is the entrance slit, number 2 the collimating mirror, number 3 the grating, 4 the focusing mirror, and 5 the detector, which could be, for instance, a photodiode. So by turning the angle of the grating, you can select basically the wavelength which is detected. In comparison, an array spectrometer uses an array detector, which could be a CCD or CMOS array, and due to this, you can measure multiple wavelengths simultaneously, so no rotation of the grating is needed. Here you can see the cross-tutorrial design. This just to show you that different designs also in the optical path are possible. The advantage of this design is that it's more compact, but you have crossed optical arrays, which is more tricky in terms of stray eye correction, since it's not so easy to put apertures in there. So if we look at the details of the design, we can start here with the fiber optics and an input optics, which is here and diffuser. Could also be directly mounted, as I told you before. Then we have the input slit, which is usually in the size of hundreds or tens of micrometers, or let's say 40 micrometers to 100 micrometers. Sometimes you have directly coupled fibers which have a cross-section conversion. So the exit of the fiber, let's say, is the beginning of the spectrometer, so the input slit. We have a grating and the detector. Furthermore, we have some order sorting filters. They are used to eliminate the higher orders of the diffraction grating. Usually these filters are directly put on the entrance window of the detector. Some devices show neutral density or spectral filters in order to enhance, for instance, the dynamic range. Then we have an optical bench where all the components are fixed. We have some signal processing unit, which is usually in the range of 12 to 16 bit in terms of resolution, so in terms of the analog to digital converter. And afterwards we have the software. Again, the software is part of your measurement system. Also, if you use some DLLs. You can imagine if there is a bug that directly influences your measurement results. On this slide, we can compare a scanning spectroradiometer with an array spectroradiometer. Usually scanning spectroradiometers are bulky and pricey, so they're quite large. They're slow, since they have to scan, so it's a serial operation mode. But you have the advantage of changeable gratings or detectors. You can adjust the bandpass by different slits. Usually you have a very symmetrical bandpass function, and you have, in the case of a double monochromator, superb stray light rejection. In contrast, an array spectroradiometer is typically compact and affordable. It's fast since you measure simultaneously different wavelengths, and you have a fixed configuration. Usually also the bandpass is fixed, and due to the large wavelength range and non-scanning, you usually have different bandpass functions for different wavelengths. So the correction for bandpass effects is not that easy. And finally, which is a really drawback, is the significant influence of stray light in array spectroradiometer. In order to get a feeling for a spectroradiometer, we can have a look at the effects of the diffraction grating. So coming to the properties of the diffraction grating, we can say that we have a nonlinear relation between wavelengths and angle. So resulting, we need a wavelength calibration of this device. As well, we understand that the efficiency of the grating changes with wavelengths. So this directly shows us, okay, we need a responsivity calibration of our device. Furthermore, a grating shows some power of diffraction, so it's given by the lines per millimeter. So the power of diffraction needs to be matched with your input slit and the wavelength range. Furthermore, we have some zero order and higher orders. And this directly leads to the effect that you need some higher order filters in order to reduce this effect. And this also is a contribution to the stray light. So you may need a stray light correction. So based on the grating, we somehow get a feeling for spectroradiometers, and especially array spectroradiometers. On this slide, we would like to show you some general requirements, and these are usually application dependent. So you need some entrance optics, which is appropriate for your measurement quantity. Furthermore, your device should be stable and reproducible, depending on the quality, what you need in your application. The next requirement is an immunity against ambient conditions. So for instance, if you measure outdoors, you may need some temperature controlled unit in order to reduce measurement uncertainties. You will need a linearized response and some adequate stray light suppression or correction. Furthermore, you should think about bandpass or bandpass correction. And you need an up-to-date and valid calibration of your wavelengths and responsivity. So depending on your application, some of these requirements are more important or less important. But at least this is a list where you can think about for your application. In the next slide, Peter will show you different characteristics of the spectroradiometers. So this first section was important to give you a feeling for these devices and the different aspects, and now Peter will give you much more information and details about the characteristics.
So if you want to use your spectroradiometer for spectroradiometric measurements, you have to know a lot about your instrument. So you have to characterize it. Today I'm going to give you a few details about, well, the optical bandpass, wavelength calibration, dark spectrum, dynamic range, linearity, the so-called internal stray light or stray light suppression, stability, aging of instruments, and sensitivity with respect to ambient temperatures. You will need all those characteristics as a basis for measurement uncertainty evaluations when you do a radiometric calibration of your instrument. One important parameter of your system is the spectral resolution or the bandpass. If you have monochromatic radiation like from a laser line, you get a line spread function. So the signal is spread over several pixels of your spectroradiometer, not only to one wavelength. One important parameter of this line spread function is the so-called center of gravity or centroid wavelength. And if you then flip the shape of the curve around this centroid wavelength, you get the bandpass. And the area under this bandpass curve, if you form it into a rectangle, gives you an indication about the bandwidth and therefore the spectral resolution of your system. So if you want to have a small resolution, which results in a narrow bandwidth, then this may increase your measurement time because the signal is getting lower. So you have to find the right bandpass bandwidth for your system. And always keep in mind that this bandpass is somehow manipulating the signal or the radiometric unit you want to measure. So slopes may be widened and peaks may be flattened. And also the asymmetry of your bandpass function, which is always present in array spectroradiometers, may cause a kind of wavelength shift of your instrument. The bandpass function of spectroradiometer usually changes with wavelengths. In this example, you can see how the asymmetrical bandpass function changes from shorter to longer wavelengths. This is expressed by the difference between center of gravity wavelengths and peak wavelengths. If you want to know more about bandpass correction, you may have a look at this following CIE document CIE 214. The raw data of an array spectroradiometer is usually expressed in counts per pixel. But we want to have an assignment to wavelengths, and therefore we need reference spectra. We could use several so-called panel lamps with atomic lines, or we have known lasers that we can use, or even we have a tunable laser and then a calibrated wave meter, or we use etalons or absorption filters or other reference spectra to assign a wavelength to the x-axis of our instrument. So let's see how we can perform a wavelength calibration using different lamps with atomic lines. So you may need several different lamps because you want to cover the whole spectrum of your instrument. So for example, here we have 3 lines like mercury, argon, neon and xenon or krypton to calibrate the system. And you can do measurements at several integration times, and you should always subtract dark current. After you have performed such measurements, you have to find the right lines to assign a wavelength calibration, and this depends on the bandwidth of your instruments. You should avoid double emission lines within the bandpass of your instrument. You have to find the right wavelength assignment, and we always recommend, as I already said, use the centroid wavelengths, the so-called center of gravity. So after we have found some lines and assigned wavelengths to the peaks, we can then perform a polynomial fit to get the whole wavelength scale. And you can see that the second order polynomial fit is already sufficient for many calibrations. It's very important that you avoid extrapolation, because this would lead to very misleading results. You should never forget to measure the dark signal, or better, the dark spectrum of your spectroradiometer. It's unique for every array and it changes with integration time. It's not enough just to subtract an offset. You can see that you have local differences in the dark signal. You may have temperature dependence, it may drift over time. So we would recommend that you measure the dark signal every once in a while, at least every time you change integration time. The dynamic range of your instrument depends on the ADC resolution, the selectable integration times, the noise level of your detector, and the throughput of your instrument. You may enhance the dynamic range by using measurements with different integration times. Or you can use neutral density filters to attenuate the incoming radiation. But be aware that neutral density filters usually are not neutral, so you have to know the transmission curve very well, because especially in the UV you can see that the transmission changes by about 2% per nanometer. Ideally, there is a linear relation between the incoming radiometric quantity and the measured signal, but in reality we are always facing nonlinearity effects. These effects might be due to the detector or the electronics, and sometimes the real integration time differs from the stated nominal values. To perform a nonlinearity characterization, you should use two different approaches. One is to use radiometric variations applied at a fixed integration time, or you have a fixed input quantity and you vary the integration time. Several methods are available, like the double aperture, double beam method. You can measure relative to a linear detector, perform variations based on the inverse square law, or you use the so-called differential spectral responsivity method. Linearity corrections can then be applied as a function of counts of your instrument. Let me show you how we realize the setup to perform measurements relative to a linear monitor photodiode. We have several stable lasers at fixed wavelengths. A variable neutral density filter wheel can attenuate the incoming radiant power and therefore allows us to set or vary the irradiance on the input optics. Next, a microarray beam homogenizer produces a nice uniform irradiance field illuminating the entrance optics of the spectroradiometer. And a beam splitter reflects a fraction of the incoming radiation to a linear silicon photodiode used as monitor detector. Using this setup, first we use the integration time method, where we have a stable irradiance level and we vary the integration time. We start with a high count level at a long integration time, and then the integration time is reduced stepwise. When the measured signals are normalized by the integration time, we should get a constant count per second value at each pixel. But here in this example we can see that it is not constant, and this indicates the nonlinearity. We perform measurement series starting at different irradiance levels and so at different starting integration times. If we have a look at the deviation from linearity of these series, they look very similar, and a polynomial fit can be calculated for the deviations with respect to the measured ADC counts. Then we carry out the same procedure with the irradiance method. Here we first set the irradiance at a fixed integration time in such a way that we get a high count rate. Then the irradiances are gradually reduced. If the measured signals are then normalized with the irradiances, we should obtain a constant count per irradiance value for each pixel. The resulting deviation from linearity for several measurement series look very similar to the curve of the integration time variation. So a common polynomial fit for the deviation from linearity can be created. The deviations can be corrected with the inverse of the polynomial fit. We can also derive a rule of thumb from the shape of the polynomial fit. Never measure above 80% of full scale. Stray light is always present and has always to be considered. It can be a strong contribution to your systematic deviations. On the one hand, you have external stray light from inside the lab that can easily be avoided or corrected for. But internal stray light inside your instrument has always to be considered. Internal stray light means that you have a portion of optical radiation that reaches the detector at a wavelength position where it shouldn't be, others intended to be measured. You can easily check this by a simple method. You determine the transmission of a long pass filter, or for example OG530, with your instrument, and then you can easily see stray light. Here in this experiment we have a xenon lamp and a filter wheel, and we have the diffuser, the entrance optics of our spectroradiometers. And we perform first of all a dark measurement. That means that the filter position is moved to a blocking position. Dark measurements, as I already said, are always important. Then we open the filter wheel again. We make a reference measurement at 100% transmission here of a xenon lamp. And then we move to the filter position of OG530 and perform a third measurement of this filtered radiation. Right after that, we calculate the transmission. And you can see here at 250 nanometers we have a stray light in the range of 30%. And if I compare this to the nominal transmission of this filter, you can see all this seen there in the light blue curve below, let's say 450 nanometer. This is due to stray light inside the instruments. It is important to know that a fraction of the signal at every wavelength is caused by stray light. Of course, this stray light is dominant in the spectral range where the quantity to be measured is low. So for the xenon lamp, or here in this example for a halogen lamp, in the low spectral range, in the UV spectral range. This also means that the stray light amount strongly depends on the source, the relative spectral distribution you have. If you have two sources of the same relative spectral distribution, then the stray light contribution will be the same. But if you have different sources, then you will have different relative effects of stray light. So it's not so easy to correct for stray light. You cannot simply subtract an offset also. If you want to characterize the internal stray light of your instrument, you can use a tunable laser and measure line spread function and stray light distribution at several different wavelengths. The reasons for internal stray light can be scattering from optical components. The zeros diffraction order produces a lot of stray light, double diffraction, higher orders, grating ghosts, interreflections, scattering at order sorting filters usually directly on the detector, and even the fluorescence of your entrance optics. What you get is a signature of your instrument, and this is usually stable, so it remains if you don't change your instrument. And by knowing this stray light signature, you might correct for. But always keep in mind that spectroradiometer includes also your entrance optics, and this can have a huge effect on your stray light signature of the instrument. In this example, you can see that a barium sulfide integrating sphere produces a lot of fluorescence stray light, and this might also be temporally dependent. If you have measured a lot of line spread functions, you can correct for internal stray light by producing a stray light correction matrix. So you have this line spread function at a certain pixel, and you have the stray light distribution function at other pixels. You can put all them together in a stray light distribution matrix, and together with unity matrix you invert it and you get the stray light correction matrix. This stray light correction matrix is then multiplied to the vector of your signal, to the spectral measurement, And as you can see, you can get a significant correction, especially in the UV spectral range. If you don't have the possibility to produce a stray light correction matrix, you might use other procedures to correct for stray light or just even to avoid it. So you might use spectral filtering to avoid stray light generated from outside the spectral region of your interest. You might use bandpass filters to divide it into small spectral bands you are going to measure. Or you use this out-of-range stray light filter method where you have long-pass filters. Stray light is always present in the UV, in the blue to UV spectral region. This is where you always may have to correct for stray light. Check the stability of your instrument and the repeatability of your measurements. As already mentioned, the dark signal will change by time, as well as the spectral responsivity may change or drift. Many fiber-coupled instruments have so-called SMA connectors. If you remove and reattach those connectors, your system might significantly change. So we would recommend after calibration you should not remove the fiber from the instrument. Or you can use fibers with so-called FC-type connectors which are coded so that the reproducibility of reattaching them is very, very good. The responsivity can be checked using a portable calibration source, so in the field, or what we also would recommend that you recalibrate your instrument directly before use. You can easily test your instrument. You have a stable lamp source, you do not need absolute values, and then you reattach your fiber optics and see what happens. You should also have a look on bending your fiber optics. Does this have an effect on your measurements? Does this change the measurements? Be aware that the mechanical mounting can have a really huge effect on your signal or signal change, so always take this also into account. The wavelength scale itself might also not be stable over time. So it may change, like in this example, it changed by 0.2 nanometer per year due to instrumental degradation or aging. So you should always check the wavelength calibration of your instrument from time to time. Changes in the ambient temperature can also have a huge effect on the measurement results. Therefore, you should characterize the temperature dependency of your instrument and keep in mind that many parameters can be influenced by temperature changes. For example, the dark signal, the signal noise, the wavelength scale, the bandpass, or the spectral responsivity. Therefore, the temperature coefficient you will get will be spectrally dependent. And as you can see in this example, temperature changes can have a huge effect on your measurement results. Therefore, we would recommend that you use a thermostated detector or better a thermostated instrument to avoid temperature dependencies of your measurements. Let us have a look at the measurement procedure itself. Here I demonstrate how to measure a tungsten halogen lamp to calibrate the spectroradiometer. First of all, the input optics is installed and adjusted in a given direction and at a given distance to the standard lamp. To make sure that the possible external stray light is reduced, black walls and apertures are mounted. After switching on and warming up the lamp, the appropriate integration time is set and several measurements are performed. The dark measurement is done here in such a way that only the direct radiation of the lamp is blocked by shading. In this way, dark signal contains the remaining external stray light and can be subtracted from the measurement signal. Further measurements with other standard lamps, for example with a deuterium lamp, may be necessary if a complete calibration is performed. The data processing then takes place in several steps. First, the dark signal is subtracted from the measurement signal. Then the correction with the nonlinearity is carried out using the previously determined polynomial. Then a normalization with respect to the integration time is carried out, followed by the wavelength assignment for the pixels. For high-quality applications, a correction of the internal stray light and possibly also a bandpass correction of the measurement is then carried out. The conversion into the desired spectral quantity, radiometric quantity, is then performed as the final step by applying the calibration data of the spectroradiometer. How these data are determined, I will explain in the following. Among other methods, the so-called source-based calibration method can be performed. For this, we recommend using a set of up to 3 standard lamps. The measurement setup should have easily reproducible conditions and low external stray light. Multiple measurements should always be carried out repeatedly. After calibration, the configuration of the system should not be changed. I would say it must not be changed. The standard lamps should be selected appropriately for the intended application of your instrument, and the calibration might be verified using other standard lamps. The responsivity of the spectroradiometer is mainly the ratio of the corrected measurement results divided by the known spectral irradiance of the standard lamp. This equation is extended by several adjustment factors which take into account the influences determined during the characterization. If they have already been taken into account during data processing, the factors are mostly 1. However, they all have measurement uncertainty that must be taken into account. Once the instrument has been calibrated, other lamps can be measured with it. Here the ratio of the measurement signal to the instrument's responsivity is calculated. However, the adjustment factors that occur here may differ from the factors used during the calibration, and they may contribute with different measurement uncertainties. When lamps are used for calibration that are similar to those used in the application, direct substitution can be used. In this case, the instrument is not needed to be calibrated. Only the ratio of the measurement results and the known spectral irradiance of the calibration lamps are required. Then it is possible that several adjustment factors are shortened out from the equation and their measurement uncertainty contributions can be omitted. All quantities listed in the previous equations contribute to the overall measurement uncertainty. How this is calculated is discussed in another tutorial. Many results and parameters of the spectroradiometer characterization provide measurement uncertainty components. For spectral irradiance, we have the temperature response of the instrument, the wavelength accuracy, and the uncertainty of the nonlinearity correction. The internal and external stray light that are dependent on the lamp sources being measured, and also the bandpass of the spectroradiometer has to be taken into account. And so-called geometric parameters such as the angular dependence of the input optics and the reference plane for distance measurements are included in the uncertainty calculation. The measurement uncertainty of the calibration of the standard lamp is also a significant contribution. There might be other components that depend on the measurement conditions. Therefore, it is recommended to perform a comprehensive measurement uncertainty analysis in connection with the characterization of the instrument, which we cannot go into details here. Let us now demonstrate the application of spectral measurements with a concrete example. For this, I hand over to Ralph again.
Thank you, Peter, for giving this nice and very detailed overview. On the next slide, I would like to show you some considerations for applications. So, the application which I have chosen are solar UV index measurements. The UV index is a standardized dimensionless quantity that represents the daily maximum of the erythema weighted global irradiance. Or in other words, it gives you the maximum of the erythema radiation on a specific day. Below here, there's the mathematical description. So we have our measurement here, and here our actinic weighting function. graphically shown, we can do it like this. So this is our measurement, and this here is the weighting function, and these both multiplied gives you this function here. And what you can see is that this UV contribution is the highest contribution to the UV index measurement. If we now think about stray light, we understand that if we would have a stray light level here, then this will end up with some high signal down here. And resulting, we would measure a too high UV index. So stray light is a systematic error during UV index measurements, and actually this error can be quite large. The next effect where we can think about is the dynamic range. So by having too large dynamic range, we would have some, for instance, noise here. So we can't resolve this solar edge. Resulting, the same will end up, we will end up with the same here. So no noise over here, and we can't resolve this. And as a result, the measurement uncertainty of the UV index will be quite large, since you have that high noise contribution here. So the noise contribution is in the same range, basically, as the highest signal contribution. Thinking about a possible wavelength shift, we will end up with a signal like this. So the solar edge in this case is shifted to the right or to the left, which will actually end up with different signals multiplied by the irreducible weighting function. So as a result, your UV index might be too high or too low, depending on the direction of the wavelength shift. So the wavelength shift is a systematic error. Diffuse lights are actually of importance in order to understand and or to explain you that you have to consider these characteristics for your application. So the wavelength shift is important for this UV index measurements. So you should not have a wavelength shift, since it's a quite large measurement uncertainty contribution. But maybe in a different application, this effect is not that highly pronounced. Also stray light. So you have to think about your effects in your application, and you have to make a specific measurement uncertainty determination.
Thanks, Ralph, for the illustration of the challenges of such an application. So let me summarize. To evaluate the effects of optical radiation, spectral measurements are often necessary, and for this, array spectroradiometers are usually used. Although they are easy to handle and to operate, they still require a careful characterization with respect to some critical parameters. And we have to keep in mind that each instrument is different, even if they are of the same type or design. And if we do not know these characteristics, it's not possible to perform a reliable calibration or a robust measurement uncertainty assessment. Please remember these 3 rules of thumb. Always measure the dark signal, never exceed the 80% level, and internal stray light is always present. If you need further information, you can find them in the document listed here. And finally, let us thank you very much for your attention, and we hope that we have explained the topics to you a little bit. Thank you very much.